5th anniversary of the Colloquium. And on October 1998, Pat Allaire gave the first Colloquium talk. Of course, we had a small service interruption during COVID, but we're having a reasonably full schedule this year. Larry D'Antonio is speaking in April. Jimena will be speaking possibly February, possibly March. And we expect actually to have a pretty full schedule in the spring semester. Hey, Pat, how are you? Good to see you. But right now, it gives me great pleasure to welcome Maria Zack. Many of you know Maria. She's at Point Loma Nazarene University. She was past president of the CSHPM. She is past president of the CSHPM. Undergraduate and graduate degree from UC San Diego. San Diego is such a beautiful town.
It's a terrible place. Somebody's got to live there.
And she's come all the way to the East Coast to tell us about Blaise Pascal's cycloidial contest. Good.
All right.
Maria, thank you.
Thanks. All right. So I'm going to talk a little bit about a contest that Pascal held and some connections to it. And so let me give you just kind of a little bit of background about where this is coming from. Is for the last few years, I've been working slowly on a project about the history of the cycloid. So I've been trying to understand. I got interested in it, I don't know, maybe like 8 or 9 years ago, just because I kept tripping across it. That a lot of famous mathematicians had worked on the cycloid, and it's a, such a simple kind of curve to discover and to think about. But it turned out it was everybody's favorite example in the emergence of talking about calculus and things like that. So I've been slowly working on this project. I first talked about this a number of years ago, and Fernando Gouveia came up and said to me, "I think there's a book in this," and he started describing to me sort of the outline I had in my head, and then. Glenn Van Brummelen, every time I see him, asks me if I have gotten any further on this project despite all the administrative load I have. The answer is generally yes, but incrementally. But one of the things I struggled with was trying to figure out what's the organizing principle for telling this story. And I finally realized when I started working on what Pascal had done with the cycloid that this actually provides what I think is the organizing principle for telling the story. So you guys are a little bit of guinea pigs in terms of me wanting to talk about how do I want to organize this sort of interesting tale of who worked on the cycloid and how and why. So I'm going to start by telling you about the contest that happened in 1658. And then I'm going to talk about some other people who worked on the cycloid that were in some way connected to this contest. This is really why I started to think about Pascal as maybe giving me the organizing idea here. All right, so let me just talk a little bit about this. So in 1658, Pascal publishes a contest, and we'll talk about the contest, and then a series of, when I say publications, we're talking about sort of pamphlets or things that were circular. It's not something that would be recognized as a journal article or anything that was sent far and wide. And there's this lovely legend that he had a terrible toothache, and to distract himself from the toothache, he worked out all these solutions to the cycloid. What is important about this is that by 1658, Pascal was not really doing a lot of mathematics anymore. This is the period in which he had gone back into really mostly thinking about theological kinds of topics. So this is sort of his last mathematical diversion before the end of his life. All right. And what he does is he poses a series of questions as part of a contest with a cash prize, but he does it under the pseudonym of Amos Dettonville. All right, so let me tell you a little bit about the challenge. So this is in June of 1658. He puts out a challenge and he says, all right, this is what they want. He wants the contestants to answer. The area of the cycloid, the center of gravity of the cycloid, the volume of the cycloid if you rotate it both around the x and the y-axis, and then the centers of gravity of these two solids and parts of these solids. All right. There's a wee bit of a problem with this, okay? The challenge gets sent out very far and wide, and we know a bunch of people who received it, not all of whom responded in any way. all right? But what's happening is that there is a gaping hole in Pascal's knowledge, all right? So these are some of the contestants that it was sent to. So Leibniz, Huygens, Wallace, Wren, people you would know, Van Schooten, René Desluys, which I'm going to talk a little bit more about, and I do not speak French. You probably have already discovered this. Antoine de Lelouvre, who's really going to feature in this story. All right. So these are the people that we know for sure had contest with, or connections with the contest. The problem is that Pascal was missing all of the stuff in the blue. All right. This was all of the work that had happened well before 1658. All right. So like I said, this is in the period of time where he is thinking theologically and not really thinking about mathematics. But it fits into the description of the contest. So what happens is that he poses the contest, he has this collection of information he doesn't know, and nowhere in any of this is Cavalieri mentioned, although Cavalieri sits underneath pretty much anybody's solutions to the problems. All right. All right. So there's some important pieces of work that I want to talk about, but probably the most important in terms of the formulation of the contest is work that was done by Roberval, Fermat, and Descartes in response to a communication from Mersenne. All right. So the bottom line is that in this communication between Mersenne and these three, all right, the tangent to the cycloid was already known, and this is in the 1630s. Tangent of the cycloid is already known, the area of the cycloid is already known, the center of gravity of the cycloid is already known, and the volumes of rotation of the cycloid are already known. Okay. Pascal is in communication with Roberval, who shares with him that a bunch of the elements of his contest are already known. So the contest ultimately will get restated. All right. So I mentioned that Mersenne had asked Fermat and Descartes about the cycloid, both the quadrature and the tangent. Roberval and Fermat were in communication. And so then Roberval gets looped into this conversation in 1638 and is one of the three different solutions that goes to Mersenne. And these three different solutions from Fermat, Descartes, and Roberval are all very interesting and quite different. Partially because the three of them are thinking about what the cycloid is in slightly different ways. In a little bit, I'll talk about how Roberval was thinking about the cycloid. All right, so what happens is, remember, first challenge from Pascal in June of 1658. Now in July of 1658, it's like, okay, contest has been modified. We're only looking for just the centers of gravity of the solids of revolution and pieces of the solids of revolution. Still has a deadline of October 1st, but all that has to be turned in by October 1st is the answers, not the computational details. Okay. And again, remember this stuff is happening sort of in pamphlet type publications. So what you're going to see is that people were responding to the original contest because the modified contest information hadn't necessarily reached them right away. Okay, so who in some way actually involved themselves with the contest? All right, it's these five. It's Wren and Wallace and Huygens, Louvre and Desluys are the ones who involve themselves, and I'll talk in a minute about what I mean by that. All right, so let's talk first about Desluys. Flemish canon was, again, one of the, in conversation with many of the people in the period, including Pascal, Wallace, and Huygens. He did calculate the area, so remember, he doesn't know that the contest has been changed. Calculated the area, communicated that to Pascal in July, and says, by August, I really don't have the time for this contest. Okay? I don't have time to think about the rest of this. It's too hard, don't have time. All right, Huygens, all right. If you're not familiar with him, Dutch natural scientist, also very well communicated or connected in the scientific community. He finds a partial solution, but again says, I'm just not that interested in this contest. All right. at John Wallace. John Wallace does send in some solutions, but it's this kind of funny series of letters where he keeps correcting himself. Okay, does it and says, oh, there was a mistake in that. Here's the new, oh, there's a mistake. Here's the new answer. Okay, August of 1658, he complains about how short amount of time there is for this contest, and doesn't ever get to any kind of final solutions to all of the pieces of this. What's interesting to me about this, and I'm still digging my way through the entirety of his book on the cycloid, which notice is 1659. Okay, so it's a year after this contest. I'm trying to tie together, and I haven't gotten there yet, what I can find about the evidence of what he did in working on the solutions to this contest and how that manifests itself a year later when he writes about the cycloid. All right, Christopher Wren. Most people know Wren as an architect. Newton called Wren one of the 3 best geometers of his age. Most people are not particularly familiar with Wren's mathematics, and that's not surprising because he wrote very little of it down. All right. However, he did solve a problem with the cycloid, just not any of them that Pascal asked. Okay, so this contest triggered him to being interested in the length of the cycloid, which he did work out. All right, but even then, he didn't write it down. It was Wallace that wrote down his actual proof of it. All right, so here's the one real contender. My takeaway from this is that Pascal was not really a very nice person. Because I'll talk a little bit about what happens with Leloure's participation in the contest. But Pascal took the kind of sharp words that scientists had with each other in that period of time, to a completely different level in this situation. Right. Okay, so this is a French Jesuit priest, and in the end of July 1658, he sends solutions to the first 3: the area, the center of gravity, the volume of the base solid, so the easier one, the solid that goes that way. All right. So then in September, Pascal starts actually communicating with him and sort of reveals that it's him rather than this Dettonville guy. Right? And he basically says, yeah, you're pretty far from the centers of gravity solution. All right. In September 11th, Leloubet sends his volume of the axis solid, so the one that's going this way. And here's the snarky sort of response from Pascal. I'd very much like to know how you arrived at it, for finally Monsieur de Roberval, who is certainly very skillful, took 6 years. Okay, snark. By mid-September, Leloubet is also sending in the centers of gravity. He realizes, though, he's made a mistake. Okay, he realizes after he sent it in, he's made a mistake, and he sends a series of letters saying he's made a mistake, he wants out of the prize. Okay, that he's realized that he should get out of the contest. Okay, so now we get a series again of pamphlet-type publications from Pascal. So these sit in his collection of complete works, but I'm still trying to track down how far they circulated and how quickly they circulated. Right? So there's one from October 7th where he is basically talking about the structure of the contest. You know, that people are trying to manipulate my words. Some of this being, what did October 1st really mean? Like, was October 1st when you mailed the answer, or was October 1st when he received the answer, and October 1st where? And that's kind of what this communication is about. So he basically says he's established that it's a fixed date, a fixed place. The place is Paris. The day is the 1st of October. The contest is over. All right. Okay, then October 9th, he publishes something else that says, again, the contest is over. I'm not going to accept any more answers. And since he, the person, cannot win the honor of the first discovery after we publish the real calculations, he will try, after being informed, to attain at least the glory of correcting his errors. Okay, so still in October 1658, the next day, what gets published is his history of the cycloid. And in this, he says, okay, Mersenne is the first person who noticed the curve. Okay, Galileo appears to have perhaps had a prior notice, but Mersenne is the first person who noticed the curve. Roberval is the first to compute the tangent, the area, the center of gravity, and the volume of the solids. Rennes is the first to compute the length. Interesting, he gives Rennes sort of acknowledgement here, even though Rennes found something that wasn't part of the contest. And Pascal is the first to compute the centers of gravity of the solids and semisolids. Right. There's no solutions there, just...
If we're looking at the solid that's rotated around the x-axis, isn't it kind of obvious that the center of gravity is the midpoint on the x-axis? It's just a matter of demonstrating that?
Yeah, I think it's a matter of demonstrating, yeah. Okay, so here's some curiosities about this history from October 10th. First of all, he accuses Torricelli of plagiarism. Okay, which has, Torricelli's dead, all right? It has nothing to do with what's going on with this contest, except that it appears that Torricelli and Roberval may have had a bit of a conflict that has somehow crept into this contest, okay? So he has accused Torricelli of plagiarism. Nowhere, anywhere is anything about Cavalieri mentioned, and yet I'll show you a bunch of the methods. You realize that's honestly what everybody is hearkening back to. And he proposes 3 more problems with a deadline of December of that same year. Nobody appears to have taken him up on the 3 more problems. Okay. So in November 25th of 1658 is when the final judgment of the solutions has arrived. And this is, Carcavi was the person who was supposed to be receiving the things on behalf of Dettonville. And it says, both Wallace and Lalouvrée were found to not have solved the problems. But remember, both of them basically set him out of it. Okay. All right. So then he publishes, in December of 1658, a sequel to the history of the cycloid, published a mere 2 months ago. No solutions still are given. Okay, no computational explanation of anything is given. But he starts making mocking sort of statements. Right? This is what I'm saying. It's just like, I was really disappointed in Pascal when I started reading this stuff, because he takes it to kind of another level. Okay, and it's finally in a letter, the letter from Monsieur Dettonville to Carcavi, behind Dan's name, where in this letter, December 1658, January 1659, usual date issue, that where his solutions and proofs are. Okay, I am, however, not going to tell you about Pascal's solutions today. All right, what I am going to tell you about is a couple of these other attachments. So I'm going to give you a look at what Roberval did for the tangent. I'm actually going to give you a look at what Torricelli did. Right. And I'm going to give you a look at what Rennes did because, oh, one of my arrows fell off. I'm going to give you a look at what Rennes did because it's just so clever. Right. All right, so let me start with Roberval. Roberval has a really interesting sort of way of thinking about the cycloid. And what I would say is he thinks about it kind of like a physicist. Right? So he is thinking about the cycloid rather than, the way that I would describe it to anybody who asks me what a cycloid is say, take a bicycle tire, put a dot on it, roll the tire forward, and watch where the dot goes. Right? Okay. That's not actually how he thinks about the cycloid. He thinks about the cycloid as a spinning circle that's sliding. Okay, so it achieves the same thing, but this is what I'm saying, it's kind of a physicist's thinking about what's happening, is that it's somehow the axis of the circle here that's sliding along and the circle is rotating, right? Okay, so, and this is a kind of funny, it's a funny way to think about it, but you'll see that this really does sort of geometrically do the right thing, right? So a lot of the arguments that we're going to talk about with the cycloid have to do with the fact that if I'm thinking about the point A prime here on the cycloid and where the wheel is there to get to A prime, if I were to roll the wheel backwards, A prime would land here, okay? So he's thinking about how something is sliding from side to side and sort of the horizontal increase of the circle when it's spinning. It's a very strange way of thinking about the cycloid, and I have to say that I had to stare at it for a while, but it does play into how he thinks about creating the tangent. All right, so how he thinks about creating the tangent is he says, let's take a line that's going sideways, just pick it at our point, it's parallel to the base AX. Then we're actually going to hit a tangent to the circle at the point that we're interested in. Okay. All right, and what he says is the direction of the motion of xz on AX is AT. So this is actually, he's thinking in some ways of it being like a vector. Okay. And he is thinking about AR in the same kind of way. And so he does what we would show students in sort of multivariable calculus, which is he completes it. He adds the two vectors and says, voila, you get the tangent. Okay? But this comes from thinking about the motion this way and the motion of the circle spinning. All right? And a lot of his computations lean into this slightly unusual thinking. Fermat and Descartes' work on this stuff also has some kind of interesting thinking about how all three of them are conceiving of the cycloid, how the cycloid is generated in slightly different ways. All right, so there's our vector. All right, I want to talk a little bit about Wallace and Wren because Wren's length, the computation of the length of the cycloid is a little surprising. And what I would say is it's a little surprising because we're all so used to these. It's a trapping, kind of an Archimedean, something outside, something inside kind of a trapping argument. We're so used to thinking about how this stuff goes that your brain thinks it's going to go a particular direction and then it makes a left turn and does something completely different from what sort of you were expecting. So that's what I want to show you. There's a bunch of geometry, and I've done very much the draw lines in kind of explanations of the geometry, and you're going to see a spot where I'm going to wave my hands about similar triangles because you really don't want me to walk you through all these triangles. Okay, so Wren is interested in the arc length, the length of the curve itself. And remember that it's Wallace that writes it down in his book, but Wallace is also very, very clear in his book that this is Wren's argument. Okay, so the answer, the length of the cycloid is 4 times the diameter of the circle that generates it. Right? Now, he is going to be interested actually in half a cycloid. Right? And this is a crazy mess. So the cycloid that he's interested in is this piece here, the semicycloid, the half the cycloid, right? That's what he's interested in. And then we're going to talk about how all these circles come into it. So that this is one of those arguments that does make me scratch my head and think, how on earth did he think this up? Even in the context of the kind of geometrical reasoning that was happening at that point in time. All right, so the first thing he does is he constructs this set of proportional circles where what I mean by that is that the diameters are proportional. All right, so he's got an AM prime, that circle, semicircle here, where AM prime to AD, the main axis of the cycloid we're interested in, is AD to AC. And in each case, he's creating a semicircle. All right, the next thing he does is he wants to look at a tangent at a point T. All right, so the first thing he does is he draws a line parallel to the base here over to the generating semicircle for the semicycloid. Okay. Then he draws in this line passing through O. Okay. And then he makes the tangent parallel to that line. Okay, you're still looking at that saying, how on earth is that supposed to help us with anything, right? Okay, so what does he do from there? He creates this sort of serrated polygons. So what he does is he keeps using this same kind of construction with all of these proportional circles to get these little outside tangents, kind of lower tangent, if you will. It's going from the point down. All right. Nice, but weird. All right, so here we are. We've got these lower tangents. All right, next, we're thinking about doing something to the inside. All right, so what he does is, if this line down here is the tangent that's over here, then we use the upper part of it to get the interior part there. Okay, so he's using the same lines twice, one of them giving it the boundary on the piece below, and the exterior boundary on the piece below, and the part of it above giving the interior boundary on the piece above. Okay. And again, you are still looking at this saying, okay, seems like some kind of limiting argument, but I still am not really sure where on earth this is going. Okay, so he is going to use an argument that says, what he says here, and it'll make more sense when we look at the picture, is the curved line of the primary cycloid is 4 times the diameter of the generating circle. Let the curve of a semicycloid, he's just describing the cycloid with the letters we've used, and says the length of the semicycloid is double the length of the diameter of the generating circle. Okay. Whether it exceeds or falls short, let the difference be x. All right, so what's he doing here? He has now gotten in a situation where he has got each piece trapped. So he's got each length trapped by something he's saying is bigger or smaller. All right. So the kind of trapping arguments we're used to. Great, it's trapped. We're used to saying take more pieces, put them together, somehow it's good. Still have not got that tied it all to the diameter. All right, so what he then says is, here's a translation of the actual words, but what he's really saying now is we're going to take as many sides as we need to get this sort of x difference down to as small as we want. Right? Because here's our friend x sitting out here. Okay? Okay, great. Says everything's been tied to circles in some way. No explanation exactly where the 2 came from. So let's look at this a little bit. All right. And this was the first time that I was so sure before I started looking at this proof that it was going to use a circle somehow and cleverly get pi out of it. Pi never actually came into it. Okay? This what I'm saying about this sort of left turn, because you're going, yeah, seen this argument, inside, outside, right? All we've got are all these lines. They're not actually referencing anything about the circumference of the circle. It's just connected to lines coming off of, honestly, starting with thinking about the diameter. All right, so we've got everything trapped. It's coming off of these radiating lines that we created, remember, in proportion to each other. All right, so remember this, that we had AM to AD, so the shorter one to the real diameter and the longer one to the real diameter have the same proportionality. All right. Now, this is where I'm going to wave my hands a little bit because he starts talking about lines that are the same length, lines that are proportional, lines that are parallel. So we got lines of the same length. We got lines that are proportional to each other. And we've got lines that are the same length as AD and lines that are the same length as AC, having overshot it. And then we start getting all kinds of inscribed quadrilaterals, parallel lines, similar triangles. Okay, so I am waving my hands right now because you don't want me to drag you through all the details. But this is where we land. Okay? All this chasing around begins to tell us that we've got congruence relationships between lengths. All right? So this length is the same as that one, this is the same as that one, and so on. Okay? It has to do with the proportionality and all this similarity of triangles and parallel lines. All right. Great. How does that help us? Okay, well, how that helps us is that he is basically going to do a telescoping kind of an argument. All right? So what we want to think about is we want to think about that this line has an equivalent over here, this line has an equivalent over here, and so on. And he's basically going to take all those things and he's going to ratchet them down so that they sit on top of each other. Okay. All right, so what we've got is we've got the interior sum. We're trying to think about the interior sum. What's the length of all of those blue guys? Because that's going to give us our inner boundary for the cycloid. All right. And we use these congruences. Right? So if I now think about this ratcheting down and swinging back, if this comes back, okay, we've hit one length twice and then added something on top of it. Okay, so we've hit this twice and put the yellow one in. If we swing this one back, we put another yellow one in and something on top of it. Okay, so we've got this curious doubling going. So everything along here has been doubled, except for that. That's the only thing that wasn't doubled. Okay? So what he says is he says, okay, well then the interior estimate on this is 2 times the diameter minus that one little piece. Okay, not surprisingly does a similar thing ratcheting the red ones down. Okay? But now what we've got is we've got an overhang with the reds. Okay, so everything's doubled, and then we've got this guy down here once, everything else is doubled. All right, so the length is greater than 2 times minus this one little piece, and less than 2 times minus that little piece, or plus that little piece. So you're going to choose x to be handy. Right? And he says, okay, since we can make x as small as we want, very calculus-y kind of sounding argument, we've got it. Then the length is 2d. I mean, I will not forget, this was the very first of the cycloid proofs I worked on because I've been working on some other stuff having to do with red. And it took me a while to get my head around the proof because I was so positive there was supposed to be a pi in there someplace. And I had to let go of my belief that a pi needed to appear. All right. Okay, so let's talk a little bit about Torricelli.
So the idea, first of all, with the diagram you put us, there's essentially infinitely many pieces.
Exactly.
Smaller and smaller and smaller pieces. And then, once you know what your epsilon is, basically,
right,
only then do you set your MD, your DM prime and your CD. Right. Okay, cool.
Yeah, I mean, it's a really cool argument.
Very, very elaborate.
It is. I mean, and it is. It's one of those arguments, like I said, that again makes me sort of scratch my head about it's quite different from many of the other arguments at the time. So it's sort of like, what was the path that got him on this, right? But it's a very clever argument. Okay, so let's talk about Torricelli. Just to remind you a little bit about Torricelli. Torricelli has this reputation as being, quote, the secretary of Galileo. He and Galileo were in correspondence. He actually worked for Galileo for precisely 2 months before Galileo died. And then he took over basically Galileo's position in some way. All right, so Torricelli works on the cycloid. He works on the cycloid in the 1640s. All right. And the plagiarism accusation is that some person unknown has told Beaugrand the solution to the cycloid, the area under the, inside the cycloid. The Beaugrand told Galileo, Galileo told Torricelli, and Torricelli stole it and claimed it to be his own. Okay. Why on earth Pascal is worried about this accusation of plagiarism 15 years later is kind of just, I mean, interesting to me, other than whatever the politics is having to do with Roberval about that. So, so let me talk a little bit about the idea here. Let me stick with Roberval for a minute. So Torricelli and Roberval are in communication. There is a 1643 letter that Torricelli receives from, oh my goodness, my brain has gone blank. There's a 1643 letter that Torricelli receives that basically congratulates him on his solution to the area under the cycloid. Okay, so we do have a date that it's sometime before 1643. Galileo died in 1642. So that's where this sort of funny thing about plagiarism comes in. Torricelli and Roberval had communication with each other. What I don't know, and this is the thing that's got me scratching my head. So you can hear I've got a lot of I don't knows in all of this. But it just kind of feels like Pascal is somehow being Roberval's proxy in this accusation, because it's such a strange accusation. And if Roberval was trying to establish something about priority in all of this. All right, so Torricelli has 3 different solutions. I'm going to tell you about the one that's probably the best known. All right. I'm working on 2 others of them. Well, I've worked my way through 2 others of them. One of the 2 of them, some of you have heard me talk about because it's got a really tricky, annoying piece of Latin in it that you think you know what Torricelli should be doing, but it's not what he said. This is actually, so Dan has helped me some in wrestling with the Latin to try to, because my Latin's not great, and I was afraid that maybe I just really wasn't understanding the Latin. Adrian and I are now working on something with the Latin on this second one, thinking that we've got something plausible for this. So, all right, so let's talk about this is the one that actually has been translated into English. That's why it's the one that people have most often seen. All right. And it's definitely got a very Cavalieri kind of an approach to solving it. All right, so this one looks pretty because I had a undergraduate working with me who wanted to learn something about GeoGebra, so she put this into GeoGebra for me. Okay. It's funny, I've decided I think my drawing is terrible, but I think I actually like working on top of the old diagrams as opposed to redrawing things into modern stuff. So I've realized that I'm kind of happier, I think, coloring in old things. But we'll go with this set of pictures because they're pretty. Okay, so what you've got is the 2 points are created, the I and the H, which are equidistant from the center G of the diameter. Draws some lines all parallel to the base, out of those 2 points and out of the point C at the top. Okay, it is important that B and L touch the cycloid. It is important that M be a length shorter than the length of the semicycloid we're looking at, because what's going to happen is a bunch of circles are going to get laid down. All right. So we're putting a diameter in, we're putting a circle in that's tangent to B, all right, or I'm sorry, tangent pass through B, and we're putting another circle in whose diameter is at M, And recognizing that that things are parallel, right? That these lines here are all parallel to each other. Okay, so now we've got to think a bit about what's going on with a bunch of lines. And it's going to look, again, kind of like it's going to very much look like eventually like a Caligari kind of an argument. But we're going to start with just sort of thinking about a bunch of this is initially going to come from just thinking about parallel lines. Okay, so because of where these pieces are hitting on the circle, right, we know that they are the same length because of the parallelism, right? Because of the fact that we are equidistant from the center of the diameter. All right, now we need to think a little bit about how things are generated. All right. So how things are generated, and again, this is this idea of rolling and unrolling. Right. That's going to become part of our conversation eventually. So we're thinking about the arc here, BO, and the arc here at the bottom, LN. Right now we're just thinking about the arcs being the same length because of the fact that we've sliced circles in the same location. Right. We're going to draw a triangle. That triangle eventually is going to become part of our area computation. All right, and then we're also, again, going to think about a diagonal line on two parallel lines. It's these parallel these directions, so parallel in the horizontal, which gives us CR and UA being the same length. All right, now we're going to think a little bit about the geometry of the cycloid. So it may be that the easiest way to think about it is to think about this semicircle here, the FDC. If that thing unrolls, C is going to come down and hit A, right? So what we are getting for the definition of the cycloid is that this length here is the same as the circumference of the circle that's generating it, or of the semicircle that's generating it, right? If you just think about the geometry of unrolling. Okay. So what do we know? If we think again about the geometry of unrolling, LN, the arc, is the same length as AN, because when you unroll it, L is going to go down to A. All right, so now this gives us some interesting things when we start thinking about how we thought about those arcs before as having something to do with lines that were parallel. All right, and that's kind of where we're heading. So if this arc and that piece are the same length, right, then the remaining length here must be the remaining circumference on the semicircle. And similarly, this length must be the same as a semicircle going up to B. Again, thinking about this unrolling definition. So when I put all of that together, what I get is that the remaining piece of the length, which is PF, is the same as the arc length of the remaining piece of the circle. Okay, so this funny little arc is the same as this length here. It's the same size as that arc as well. Okay. Again, I'm chasing a lot of stuff around without any clear point yet about why I care, but it's coming really soon. Okay, so we're now going to do some chasing with some similar triangles. All right, PF has to be the same length as AN, and we know that because the little arcs are the same. Right? All right, so now we're going to look at some triangles. So we're going to start by looking at some properties having to do with parallel lines, and we're going to think about parallel in a couple of different ways. Now what we're thinking about is that this diagonal here is the transversal on these two parallel pieces. We're thinking about the vertical parallels here. Okay, and so what we know is that CS and AT are the same length. All right. We also know, by thinking about parallel lines in the other way, all right, We're gonna keep having to think about vertical parallels and then horizontal parallels, kind of going back and forth to do this. All right. So we also know that CH. Let's see. No, that's. Let's just focus on these two long ones. I'll go jump to the smaller guys in a second. Okay. So jumping to the smaller guys now. We have RS is equal to UT, since we know that the big length AT is the big length here, and the smaller length are the same because of parallel sides, or parallel lines. All right, again, why do we care? It seems like something just kind of floating out in the middle of nowhere. Right, more triangles. This is now actually something we care about. This length UQ is the same as the length XR. Again, coming from similar triangles, now these little guys. And now here's actually the point. Okay. The point is that LU plus BR, so going from here all the way across to that point, is the same as LU plus BX plus XR. And we know that XR is the same length as QU. So what we've got is this is LQ plus BX, and that LQ is the same size as AN, which is the same size as EI, which is the same size as D8. Oops, as XH. I just realized there's a typo there. Oh no, that's right. EIDH. Yep. Okay, again, why do I care? Still, why do I care? All right, I want you for a moment to focus on the kind of loon that's outside of the triangle. So the upper loon. So what you've got with the upper loon is LU down here and BR up at the top. So you've got two parallel lines sitting in that upper loon. Now if you look at a semicircle, what we know is that those two red lines are the same length as the two yellow lines. And so what we've got is we've got these lines in the upper loon that can be tied back to lines inside of the semicircle. And if you now were to use a Cavalerian kind of an argument, where I put a new parallel in here and here, I'd get a different set of lines that traced out some spots in the semicircle. And so as you move the lines up and down, you fill in the loon with lines, and you fill in the semicircle with lines. And what you end up with then is that the size of the loon is the same, the area of the loon is the same as the area of the semicircle. It takes a while to think about it. Yeah, it's so, but all of a sudden you realize now that again, this is looking, Riemannian is anachronistic, but it is looking a little bit like the way that we would describe to students how you can see that the area of two things is the same, right? Is that I can keep taking slices that match with other slices. And he says, okay, yep, that's exactly right. Then the loon, that funny loon, is a half a semicircle. And then the rest of it's really easy, because now you've got the triangle here, right? Which is the circumference times the diameter times 1/2, right? So you end up with two more semicircles. So there we are, 3. And that's the end. And it's 4:56. All right.
Thank you. We have time for questions. That would include if anybody from Zoom would like to ask. Question over here from Pat.
What was the prize?
40 pistoles, or pistolas, or however you pronounce it. And of course, nobody won it. It's also a little bit unclear where the money was supposed to come from.
Oh, yeah?
Whether it was Pascal's money or the money was from somewhere else. That's one of those things that nobody seems completely definitive on because nobody won.
Now, when you had the diagram up of the people, it was only the ones on the left, the line on the left that had actually submitted solutions, correct?
Yeah, so the ones on the left, let me see if I can do this without making everybody crazy. Whoops, overshot, there we go. Yeah, so these are known recipients, and there's probably more, okay, but these are known recipients. It's only this group that seemed to actually engage. So like the other two, Leibniz, Van Schooten, seem to have received it, but not engaged in communication about it, okay? And then, you know, we've got various levels of attempts in like, I don't have time, and then Wren, who just answered a completely different question. So and again, I'm still trying to dig through. Now that I've got a better web sort of laid out, now I'm trying to drill down into various things. I will say that the Pascal in French is, at least for me, a bit slow going. So trying to read his announcements and his pronouncements, and then to go back through what we have of his correspondence to see who else actually interacted with him.
If I may continue, so I'm intrigued on the lower right. I presume that Beaugrand is the person that brought the curve or the questions to Galileo's interest, and then Galileo it spread via Mersenne to everybody. And then who's the mystery man? That's what.
Well,
really
so all of this is unclear. Okay, I'm still trying to figure out what, if anything, Beaugrand actually did send to Galileo, right? So it's really unclear what was sent, right? And Galileo's, if you look at what Galileo says about the area of the cycloid, it was a computation based on weight of materials. There was nothing mathematical about it. It was sort of, you know, cut this thing out and weigh it, and it looks like it's 3. I mean, that was kind of the level of it. So there was nothing terribly mathematical about what Galileo did. But it certainly got into conversation with Mersenne and others, right? I'm a little bit unsure, honestly, right? Because again, Pascal says Mersenne is the guy who thought of the cycloid. Well, you know, is it even to some extent a curve that was just kind of in the air? I mean, is it really easy to actually say this one person was the person? Especially what I'm finding is because, you know, dating on stuff in this period is a little squishy, right? And then even if you can figure out when somebody did it, when they communicated it is, of course, a completely different story. Yeah. So I'm honestly not sure if it wasn't just something that was in the air. Because it's certainly, I mean, any of us can describe this curve to an elementary school kid and they'll understand what the shape is, right? So it's not unreasonable to think more than one person was just thinking about this slightly interesting curve. So.
Other questions? Well, let's thank Maria once again for